Hi, we're looking at an activity called calendar art. Ms. Picasso, sponsor for her school's art club, sells calendars featuring student artwork to raise money for art supplies. A local print shop sponsors the calendar sale and donates the printing and supplies. From past experience, Ms. Picasso knows that she can sell 150 calendars for $3 each. She considers raising the price to try to increase the profit that the club can earn from the sale. However, she realizes that by raising the price, the team will sell fewer than 150 calendars. Because if you think about that, if you raise the price, not as many people would probably want to buy the calendars. So, if Ms. Picasso raises the price of the calendar by X amount of dollars, what would be the expression for the price of one calendar? Well, remember, it's starting at $3, and if we're raising it by a certain amount, by X, then the new price would be 3 plus whatever she increased it by. In previous years, Ms. Picasso found that as the price increased, the number of calendars sold decreased. The table below shows the relationship between the price increase and the number of calendars sold. Use the data to write an expression for the number of calendars sold in terms of how much the price increase was. So let's look. We have, if they don't increase the price at all, 0, we sell 150. If the price increase is 0.4, then we're selling 140. So it's going down, right? If the price increase is 0.8, the number of calendars sold is 130. Increase is 1.2, $1.20. Then the number of calendars sold decreases to 120. So take a moment and think about how we could write an expression that looks at this. One thing to look at is how much you're going up as far as these X's are going and how this other side is changing. So if we look at this table, the number is going down by 10 each time. And what is the change over here? Well, it is going up by 0.4, or 40 cents. We're going up 40 cents. We're going up 40 cents. So let's think about this. For each increase in price, we're actually going down here. So think about the rate of change, or what would be maybe our slope, but our rate of change. How much the number of calendars are changing over how much the change in price is. So the change in the number of calendars divided by the change in price. So it's going down 10 calendars for the increase of 40 cents. So can we write that a little bit better? What would happen if I took negative 10 divided by 0.40? We get a negative 25. So our rate of change is actually negative 25. If we had actually increased a full dollar, we'd gone down 25. So we started with 150, and it's changing 25 for every dollar that we increase. Not by every cent, but every dollar that we increase. And that could have been another way to think about it. The increase of $1 would have been halfway between 0.8 and 1.2. So if we'd increased $1, how many less calendars have we sold? Well, that would be at 125. So that would have meant we'd gone 25 calendars for the increase in price of $1. Now let's think about a function for the amount of money raised selling calendars when the price is increased by a certain amount. So if we're talking about the amount of money raised, well, it depends on the number of calendars, and it depends on the price. So we have an expression for the number of calendars, and we have an expression for price. The expression for the number of calendars is 150 minus 25x, and the price was the 3 plus x, because we are increasing from $3 a calendar. And we're going to write this in standard form. Remember, standard form just means to multiply it all out. So I'm going to come off to the side. If I multiply that all out, 150 times 3 would give me 450. 150 times x gives me plus 150x. Negative 25x times 3 is negative 75x. And then negative 25x times x is negative 25x squared. Now, standard form is when you have the ax squared plus bx plus c. So, the x squared term was the negative 25. The middle term, 150x minus 75x gives me plus 75x and 450. So we're writing them in order. We like them decreasing in exponents, so x squared always comes first. Our a, the coefficient of x squared, would be negative 25. B is the coefficient of x, that's 75. And c is 450. And I want you to think, why is it important to know which ones are A, B, and C? Well, they're definitely important for our quadratic formulas and everything. So we need to make sure we remember which parts are which. Now, in the next part, we're actually going to graph this function. So before I change over, I want you to go ahead and grab your calculator and make sure that there's nothing in your y equals. If there is, just clear it out. And we're going to type in our function, negative 25x squared, and then it was plus 75x plus 450. So I went ahead and typed it in while I had my function handy. And before I do anything else, I want my window on my calculator to mimic the window that I have here. So let's look. To set up our window in our calculator, we need to know what our x minimum is and what our x maximum is. And we also need to know what the scale is. The scale is what you're counting by. Y minimum, Y maximum, and the Y scale. These are all really important to setting up your window to match what you're looking at on paper. So x minimum, this is our x-axis. We look for what the smallest x is. So that's really negative 1, negative 2, negative 3, negative 4. That would be negative 5. Our maximum x value in this picture, let's see, that's a 2, so that means that's 1, 2, 3, 4, 5, 6, 7. And what are we counting by? Well, I was counting by 1s. The y minimum, let's see. Well, that's 100, so that means that's 50. So going backwards, that would be a negative 50. Our maximum y value, that's 100, 150, 200, 250, 300, and so forth. So 600, the next one would be 650. And it seems we are counting by 50s. So we had our equation. Now we're going to make our window match the window of the problem. Right now, it's totally different. So I'm going to change it and make sure the x-min matches. I'm typing in negative 5 X max needs to match 7. X scale 1, that's good. Y minimum negative 50. Y maximum should be 650, not 12, so I'm going to change that. Y scale is supposed to be 50. And we're first just going to look at the graph and see what it looks like. Ooh, it's a parabola. And if it's a quadratic, we would expect a parabola. To make sure I graph it properly, I'd like to use the table. So I'm going to go to the table, which is second graph. And I need to start down here at -5. So I'm going to go up arrow all the way to get to -5. But wait, that's way off my grid. The first point that's really going to be there is the point -3, 0. That's going to be right here. Oh, that's an x-intercept, isn't it? The next point I could graph is -2, 200. So -2, 200. -1 goes to 350. And then 0 goes to 450. That's our y-intercept, isn't it? So let's remember, that point is called an x-intercept because it's crossing the x-axis. This point is called the y-intercept. It's crossing the y-axis. 1 goes to 500. Oh, 2 goes to 500. I don't think it's supposed to be flat there. 3 goes back to 450. Four goes to 350. 5 goes to 200. And then 6 went to 0. So there's another x-intercept. Now up here, it's not going to flatten out. I think it's going to go up in between there, because it's supposed to have a little bit of a curve. And remember, we talked about those maximum points, but it didn't show up on my table. We had a like 500 and then 500. I think it's right in between there. So there's a couple of ways I could find that that vertex that's right in between there. One way is to change my table setup. Instead of counting by 1s, if I counted by 0.5 and see if I can find it that way. So I could change my table setup starting at 0, but instead of counting by 1s, count by 0.5. Let's go back to the table now. 0, 0.5, 1, 1.5. So it changes our table, and we actually get to see a little bit more. There was 500 and there was 500. I think that the vertex was going to be right in the middle of that, because it's very symmetrical, at 1.5 and then 506. So it really is just a little bit above there. That vertex, or where the graph turns around, is at 1.5, 506.25. Now, I mentioned that there was more than one way to find that point on the calculator. The other way is, since that is at the top of the graph, that is also what is called a maximum point. So let's look at another way we could find that maximum point. Making calculations on a graph is done by using the Calculate menu, which we'd find by going second trace, and you'll notice we're in the Calculate menu. There's actually an option for maximum. The maximum function finds the maximum value of a graph. Now, it doesn't find it all by itself, though. You have to help it zoom in. Left bound means go to the left of where you think your maximum is, and then press enter. So I am well to the left of where I think it is, and I'm going to press enter. Right bound means go to the right of where you think that maximum value is, and press enter. Now it says, would you like to guess? I think it's about there. And I'm going to press enter. It now tells me my maximum is at 1.49999, basically 1.5, and the y value that goes with it is 506.25. 1.5, 506.25. We got the same thing by changing the table or by using the maximum function. Now let's see if we can use that to answer a question. What is the maximum amount of money that can be earned? Well, we just said that was a maximum point, so that is definitely the maximum amount of money. So the maximum amount of money earned is $506.25. What is the increase in price that will yield that maximum amount of money? Well, let's remember what X represented. X was the dollars that we increased by. So, $1.50 increase will give us the maximum money earned. And this is found by finding the vertex.